Hey guys, I built this 4x4x4 RGB LED cube, and in this video I'll show you how. An LED cube is a collection of LEDs that are arranged in such a way that they form a cube shape. But you could also make a similar thing in a different shape. In an RGB cube, each LED actually contains 3 separate chips. Here I show them under the microscope. If you run current through these chips, they start to emit light, each in its preferred color, namely red, green and blue. To save leads, the 3 chips in such a device usually share one lead. This is not really visible under the microscope, so you'll have to take my word on this one. This shared lead can be either cathode or anode and should be mentioned in the product descriptions you'll come across when searching for these. I for one came across some cheap common anode LEDs and decided to get them. I really didn't give the choice between common cathode or common anode a whole lot of thought, but it should be okay. It should be possible to build an LED cube with either one. In the remainder of this video I will refer to the other leads by the color the chip would produce if you would hook it up. So for example, I would refer to this lead as a red lead, to this lead as a green lead and to this lead as a blue lead. Each chip in such an RGB LED can handle about 20 milliamps. So in total that makes 60 milliamps per LED. A series resistor can be used to limit the current through a chip. When using a 5V supply, the resistance value should be about 250 ohms, but usually you take 220 or 330 ohms. Although the current through a single LED is pretty limited, if you have a whole bunch of them, the total current can actually quickly add up to a pretty large value. In our case, we have a 4x4x4 RGB LED cube. Current would be 4x4x4 times 60 milliamps if you would drive all LEDs and all colors. And this would add up to about 4 amps. And this actually is quite a lot. For this you already need quite a large power supply in comparison to such a tiny cube. And this is a good reason to not drive all LEDs at the same time. Another good reason to not drive all LEDs at the same time is that it would take a lot of signals or channels to do this. In our RGB LED cube there are 4x4x4 times 3 equals 192 channels to drive. And I really couldn't find any cheap microcontroller that has this amount of pins. So definitely a more clever mechanism for driving the LEDs is needed. To drive a cube in a smart way, it is usually split up in columns and layers. Columns usually connect a common lead, so in our case it's an anode, while the layers usually connect the other leads, in our case the cathodes. This way, per layer per column, an LED can be actuated. And to be able to control all 3 colors, all red leads in the layer are connected, all green leads in the layer are connected, and all blue leads in the layer are connected. So you actually have 3 channels per layer to drive. One for red, one for green and one for blue. With this wiring trick we must connect switches to the columns and switches to the layers. Since we have 16 columns and 4 layers with 3 colors per layer, we have 16 plus 4 times 3 and this is 28. So we need 28 switches. However, 28 pins on a microcontroller can still be too much, especially if you have decided that such a tiny cube should come with a tiny microcontroller. For these kind of cases, there's a device available called the shift register. A shift register is a very simple but useful device. It only has 2 inputs. One of those is a clock and the other one is a data line. Clock is a very simple signal that alternates between high and low. And on each rising edge of the clock, the values on the output pins of the shift register are shifted by 1, and the value on the data line is put on the first output pin, and the value on the last output pin is lost after each clock cycle. I have obtained 8-bit shift registers, and since I need 28 switches, I will need 4 of those 8-bit shift registers. For the microcontroller, this would mean I would need 4 pins to drive the data lines, and if I connect all the clock lines to a single pin on the microcontroller, I would in total only need 5 pins on the microcontroller to drive the switches. If we would, for example, choose an AT-Tiny85 microcontroller, this would fit. And according to the datasheet, this should even leave us with a pin that we can use as a button input, so we can cycle through the programs that we have implemented on the microcontroller. Now with the theory out of the way, it's time for some practice. To make the LED cube, I start with making a small jig for holding the LEDs in place while I'll solder them to make the layers. The jig consists of a simple grid of 5mm holes, of which I determined the pitch such that I would just be able to solder the leads and not need any additional wire. This pitch turned out to be 1.5 cm. Then I placed the LEDs in the holes and I bent the red lead to the front and the green lead to the back. I then solder each red lead to the red lead of the next LED and each green lead to the green lead of the next LED. This makes sort of a double line running over the LEDs. The anode leads I initially bent to the front to make room for the blue leads. I cut a piece off because later on I want to push them all the way through, out of the way of the cathode leads. After the anode leads are out of the way, I bend the blue leads to the side, making sure to put my tweezers under them to prevent making contact with any of the other leads. I then solder the blue leads, connecting them in rows in which sometimes I need to cross significant gaps with solder. Apparently some of the LEDs have shorter leads than others, but it's okay, the solder is very forgiving. In the end I connect all rows such that in one layer all red leads are connected, all green leads are connected and all blue leads are connected. When a layer is finished, I test the LEDs to make sure they all work. At this point it should still be doable to replace an LED, but when the cube is finished this would be nearly impossible. I repeat the entire procedure 4 times, making the 4 layers. Now the 4 layers are done, it's time to stack them. For this I first make some columns out of sturdy wire. I get some binding wire from my garage of a diameter of about 1 mm. Unfortunately the wire is pretty mingled, which could result in an ugly cube. To fix this I work harden the wire by clamping one side with pliers and putting the other side in my battery operated drill. This creates torsional deformation, straightening out the wire and even making it a bit more stiff. My facial expression might not show it here, but I was actually pretty surprised to see how well this works. To make the columns stand upright, I first make a base plate to insert them into. And while I'm at it, I make the rest of the housing too. For the base plate I first draw the outline and some holes on paper. Then I take an awl and put the pattern on a piece of HPL plating. I use a saw to cut it out and drill to make the holes. I also cut out some side panels and a bottom plate. And I make a slot in one of the side panels for cable feed through and a hole to fit the button in. Finally I glue everything together and I touch it up with some spray paint to make it a bit easier on the eyes. Then I glue the columns in place and start stacking the layers. To get the layer height right, I prepared a small measurement rod with markings on it. To hold the layers in place during soldering, I use some tiny magnets. Each time a layer is finished, I check all LEDs to see if they are still functional. Only after I'm convinced I continue to the next step. The next step involves connecting some enameled copper wire to the layers and bringing one end of the wire into the housing. This enameled copper wire is strange stuff. It looks like real copper, but it has a super thin layer that actually electrically isolates. So you really need to sand away this thin layer to make the wire conductive. After having soldered all 3 contacts on all 4 layers, so that's 12 solder joints, and having brought the other ends of the wires into the housing through the holes in the base plate, I first solder some regular wires to the sanded ends in the housing. I then shield these joints with some heat shrink to prevent unwanted contacts. And then I glue the hole to the inside for some strain relief. After this it's time to solder some wires to the columns in the housing. These joints I also cover with some heat shrink. Now the simple stuff is done, it's time for the hard stuff, namely making the electronics. I start with a high side switching board which switches the anodes. It's called high side switching since these switches are at the high potential side of the electronics. For high side switching you can use PNP transistors. However, I usually also use NPN transistors, since then I can switch a voltage that's higher than that of the control signal. The NPN transistors then basically switch the PNP transistors. This is desired because the control signal is usually only 3.3 volts. In this project, however, the control signal comes from the shift registers, which we supply with 5 volts. So perhaps in this project the NPN transistors might not even be needed. However, from the datasheet of the shift registers, I noticed that the drive current is actually pretty small. So I thought it might be a good idea to use this configuration anyway, as it also gives us a higher current amplification factor. I place the components and solder them, such that I end up with 16 times this circuit. When I'm halfway through, I'm starting to think that I had just better design the board and order it, because it's actually quite a lot of soldering. However, I get through in the end, and after testing, I'm happy to see that the switches are all functional. I then start soldering the high-side switchboard to the anodes. But after the first few leads, I realize that I forgot to mount the button, so I squeeze it in and mount it with my pliers. I then continue soldering wires to the anodes, and when I'm done, I test again to see everything still works. I then start soldering the low-side switchboard, which switches the cathodes. This is called low-side switching, since these switches operate at the low voltage side of the circuit. For this, I happen to have laying around 2 Darlington transistor arrays, which saves me a whole lot of space on the board, and which makes it possible to also put the shift registers and the microcontroller on the same board. Together, these 2 Darlington transistor arrays roughly do the same as the whole high-side switchboard I've just soldered, except for that they of course do it at the low side. So of course I immediately ordered some more of these. I start soldering the board, and when I'm about halfway through, I'm convinced I should have just designed a board and have it made. That would have saved me a whole lot of work. However, also this time I make it through, but unfortunately this time I don't have any method to properly test, and so I continue with connecting the board to the high-side switchboard. However, before I do so, I reckon only little room will be left for installation of any additional electronics in the housing after having installed both boards. And so I first want to sort out the power supply and some button related electronics. For the power supply, I have this small unit I found on AliExpress. It should output 5 volts and be able to deliver about 700 milliamps. This should be more than enough, since we will drive at most 16 LEDs at the same time, making only 16 times 20 milliamps, which is 320 milliamps. However, the power supply is connected directly to the grid, which is actually very dangerous. If you would come into contact with one of those bare leads, it could kill you. So I take real good care that does not happen. I make the exposed copper of the wire as short as possible, while still being able to solder onto the board. After testing, I see it outputs a nice 5.05 volts. For safety and strain relief, I put some epoxy on the joints. Then I solder some wires onto the low voltage side of the board and test again. This time I use a resistor such that the current is 500 milliamps. The power supply holds out pretty well under this load, and I apply some hot melt for strain relief, and I wrap the entire module in self-vulcanizing tape. This self-vulcanizing tape is great stuff. It's stretchy, it's tough, it does not stick, it only adheres to itself. I then shove the power supply into the housing, and it actually barely fits. I'm glad I didn't install the low side switchboard yet. Then it's time to make the signal conditioning circuit for the button. This is needed since every time I press the button I get a so-called bouncing signal. This is a problem for the microcontroller since it will interpret this single button press as multiple button presses. So to not get any unexpected behavior, I first need to debounce the signal. For this I first low pass filter the button output, which results in a slowly decaying signal, and then I use a Schmidt trigger to make a nice flank. I build this circuit on a perf board and use hot melt for strain relief and to fixate some stuff in place. It doesn't look pretty, but a little bit of tape solves that problem. When finished, I place the circuit in the housing. The yellow lead here conducts a debounced signal. Then it's finally time to solder the low side switchboard to the high side switchboard. I first connect power and ground, and then the output of the shift registers, effectively connecting the high side switches. After this I solder the cathodes of the layers to the Darlington arrays, effectively connecting the low side switches. And finally I pop in the ICs. On the microcontroller I've written a small program that cycles all LEDs per layer and per color. However, when I power up the cube, nothing happens. I do some measurements and find out that the NCLR pins of the shift registers are actually low while they should be high. So as a workaround I just solder some wires on the top to force them high. Again I power the device, but still nothing happens. What could be wrong? I don't understand, it should just work. I start measuring on the power supply and notice that we are actually a little bit out of spec for the microcontroller. The microcontroller should at most have 5.5 volts, while our power supply has peaks of up to 5.6 volts. So I straighten out the peaks using a capacitor and measure again to find an improved max value of about 5.3 volts. After this tweak, I again power the device, but still nothing happens. And then suddenly it strikes me. Did I see the word reset somewhere on the datasheet of the microcontroller? Does the microcontroller by any chance have a reset pin? And I grab the datasheet and I see the problem. Pin 5, the pin that I connected to my debounce button, is actually a reset pin. I dive into the documentation and find that I would need to burn some fuses to make pin 5 input instead of reset. However, I also read that after this I wouldn't be able to program the microcontroller anymore. So I decide to abandon the idea of using a button completely and I just cut the wire. And then it works. I have flashing lights on my LED cube. Finally! After this it's time to close up the housing. But not before I've protected the bare contacts with some lacquer, using some hot melt to fixate jumpers and for strain relief, and gluing the grid cable into the slot, and finally also soldering some programming wires onto the micro. Finally I forcefully make the electronics fit the housing and close it up using some high tech. And then the moment of truth. After all is glued in place, I test and it still works. To facilitate programming, I solder the programming wires to a pin header on a perf board and glue this onto the housing. I can directly shove the header of my programming cable onto the pins. I write some programs, but since I don't have a button to manually cycle through these programs, I just put them in a sequence. It doesn't matter, it looks cool anyway. I'll save you the code though, but if you're interested, please let me know in the comments below, because if you are, I could make a GitHub and publish the code. And that's it for this project. I hope you guys enjoyed it. If so, please don't forget to share, like and subscribe. And I hope to see you in the next one. Goodbye.